Cloud. All right, so we're started, we're recording. Everyone can hear me okay? Got some thumbs up. All right, cool. So, looks like we have a lot of new faces because I think I've seen, a lot of the people that have been coming to our events in the last year or so, and looks like we got a lot of new people. So that's really cool, really awesome to see. Um, so we are actually a brand new organization here at Quantum Computing at UCSD. We started in I want to say it must have been February actually when we kind of got started. I think we might have gone official in like March or April or something like that, right? So we're brand new. Um, so really exciting to to gear up for our fall quarter and get started and everything. Unfortunately, the Center for Student Involvement has all fall events are for at least for the first 5 weeks or so are going to be online. So if you're part of any other organizations right now, they're all going to have all their events online. So we actually went through the whole scheduling process and got a room for this event, and then found out that it would be changed a few weeks ago. So we had to kind of scrap it, put together an online event, and kind of start from scratch. Oh, so I can enable transcription. Yeah, sure. Um, so yeah, that's kind of a little bit about us. We're still kind of getting our feet, getting ourselves off the ground and getting everything working logistically and kind of putting together, a web. We don't even really have our website fully up yet, right? So just a lot of stuff going on with us. In fact, that might be an opportunity for some of you guys who, if you find this material really interesting and you want to get involved, the fact that we are a new organization, that we don't, have as much help as maybe we would need. There's definitely going to be opportunities for you guys, especially if you're, committed to putting in a little bit of work. I'm not saying 20 hours a week, but if you're putting in a little bit of work and you're helping us out with some stuff, well, there's definitely opportunities for you guys to get involved, for you guys to start maybe getting moving towards maybe even a leadership position if you guys really put in some work. So that's kind of been our experience in these last few months. Is there's been kind of a solid group of people that have really stepped up in our club, and all those people now are officers in the club. So yeah, if you guys are interested in this stuff, there's definitely an opportunity to get involved. So just wanted to kind of give a brief overview. Today we have Thomas and Ishaan. They're going to be helping me out with this workshop. Looks like those are the only officers here today. So they're going to be kind of helping me go through some of the slides. They helped us kind of put this together. So if you guys want to introduce yourselves, you can, but otherwise maybe you can do it later or maybe afterwards.
Sure, I can introduce myself briefly. Hello, everyone. My name is Thomas Sievert. I'm a third-year physics major, specifically computational physics. But for those of you in the physics major, you probably know that there's not really any difference between the different specializations.
Oh, really?
Yeah, I am currently in a research lab on campus doing research in quantum machine learning. Which is obviously related to quantum computing. So yeah, I've been doing that for a few months. I've been an officer since a little after the club started. I'm basically the secretary for QCSD. So yeah, excited to see more of you over the course of the quarter. And thanks for coming to our first event.
Awesome, thanks, Thomas. I know, Ishaan, you're in the library right now. I don't know if you can introduce yourself, but if you want to.
Yeah, I'm here. I can introduce myself. Hi, I'm Ishaan. I'm a third-year Math CS major and physics minor. If you're in the library, you might be able to see me in the corner by the chessboards. So, yeah.
Yeah, everyone come
I'm wondering if anyone's trying to look. I wonder if anyone's trying to look for me now.
All right, everyone, let's go mob Ishaan in the library.
Floor 2, the main floor.
Oh, all right, we're gonna release the floodgates. A giant
Target acquired. Oh no.
you in the library. That would actually be funny if you guys did that.
It would.
Cool. Yeah. Thanks, Ishaan. So I actually just realized we have another officer in the Zoom today. We have Kira. Kira's putting together our educational material right now. So we're gonna have a mini course coming up, which is gonna be basically a really great opportunity for you guys to learn a little bit more about quantum computing and actually dig into some of this math and some of the linear algebra and all that stuff involved. So she's putting that together. We're kind of waiting until stuff goes back to in person to put that together. Uh-oh, this library meetup sounds like it's going to happen. So yeah, stay tuned for that as well. And then and then I think that's the last thing.
Yeah, Kira's here too.
Yeah. So she's putting together our kind of educational workshop kind of thing that we're doing, our mini course. Actually, yeah, Kira, if you want to introduce yourself, feel free, but you don't have to.
Sure, I'll make it brief because it might be a little bit loud because I'm in Trice. But hi, I'm Kira. I'm a second year computer engineering major in Warren College. And yeah, I'm the educational curriculum chair. So I've been working on the mini course, which is basically aimed towards people who don't know anything about quantum, maybe don't have the linear algebra programming background needed. And we're hoping to make a course so that they can have enough background in all of that in quantum computing so that they can eventually compete in quantum hackathons. Yeah, stay tuned.
Yeah, thanks, Kira. So yeah, that should be really cool. We kind of did a informal version of that last. I guess over the summer we did these kind of study sessions where we would just kind of go watch some YouTube videos. I would try and write some stuff on my iPad and explain some concepts to the people that showed up to those. Those actually went pretty well. We got some people that didn't were kind of starting from scratch a little bit, didn't have a lot of the basics. And we're able to actually get pretty far into this subject. So I wouldn't, I think that's one of our main difficulties actually as a club is a lot of people see quantum computing and they're like, oh my god, that sounds so insanely hard. How could I ever do that? And so I'm here to encourage you guys that I wouldn't say quantum computing is easy, but I would say it's definitely doable. It's definitely you can get through all the building blocks and all the basic steps to get to a pretty good understanding of what quantum computing really is. So I would recommend you guys if you're interested in physics or machine learning and AI, or if you're interested in even chemistry and algorithms or computer science, interested in a lot of this stuff, I would recommend just checking out quantum computing a little bit. Going to some of our workshops. We have some a little bit more in-depth workshops coming up. This is very kind of general overview. So I would recommend, yeah, just check it out. Maybe come to our mini course once we get that up and running, in person, and just see what you think. If you feel like you can understand some of it and you're able to get through some of it, then yeah, I think you guys should definitely check it out. Even if you feel like it's kind of intimidating or like you're not sure if you're going to be able to do it, I would recommend, yeah, just giving it a try. So, and then I guess I said last thing. I guess we have one more thing. I just want to introduce myself real quick. My name is Ben. I started this club. I want to say I started the Discord in January or February or something like that, and just advertised it everywhere and got a bunch of people to join. And eventually, definitely not by myself, but with the help of all the officers and people that have been involved, put this club together. But yeah, I wrote the Constitution from scratch at the very beginning there, so that was pretty kind of a fun project there. So we're just in the process of kind of revamping ourselves and getting a lot more official roles and everything, and making everything more streamlined. So that's a little about myself. I'm an electrical engineering major. And I'm going to be taking some physics classes this year, so that should be fun. So let's get started. I like to start these out with a little poll. That's what kind of seems to be our tradition. So this is actually a poll. So it's a poll about polls. So I'm curious to see which poll you guys think is the best poll. So let's see. Can I start? I should be. Whoops. Should be able to start this. Oh, here we go. Okay, so let me launch this. You guys can decide what you think. Who's gonna win? So I like to use this little icebreaker, kind of a little joke at the beginning, get us warmed up. Oh, wow, fishing pole is fishing pole gonna pull out ahead? Oh. Wow, 36 people have answered. I'm impressed with you guys. We have a lot of participation today. Here, I can put this. Is this gonna show up on my? No. All right, 37 people. All right, so I'll leave that up for another like minute or two as we kind of go through the next slide or two. It looks like fishing pole might be the winner on this one. All right, so let's kind of talk about like what quantum computing entails, a little bit about what people think that we can do with it, because, and I say people think we can do about it because, or do with it because we're actually not really sure what can be done with quantum computing. It's a brand new field. It's quantum computers themselves, you know, and keep in mind the ones we have are extremely basic. Quantum computers themselves have not existed, you know, for more than like 20 years or so. So this is kind of a brand new field, a brand new technology. You know, it wasn't even quantum physics itself was conceived of in like the early 1900s or so, you know, 1900 through like 1920 or so. Quantum computing, which is an application of quantum physics, was not conceived of until like the 80s or so. And we'll talk about that. And that's actually kind of a crazy fact to me. Like it took 60 years or 50 or 60 years after they invented or discovered quantum physics to discover how to use it to for these kind of computing applications. So I think that's pretty fascinating. So as I just said, right, it's an entirely new type of computation. Some of the fields that we think it could revolutionize are like drug discovery, encryption, artificial intelligence. That's kind of a big one. That's what Google's doing. They have this big artificial, you know, Google AI project where they're doing quantum computing. And if you, you know, at least according to a lot of people in the industry, according to a lot of like, you know, analysts at like investment banks and stuff, a lot of people think that this field's going to take off. That has a huge growth potential. We'll talk a little bit later about some of the challenges as well involved in this field and why that might not be necessarily correct, but that's what it seems like most people in this industry think. So that's kind of encouraging. So the question is why, you know, why quantum? What is so special about quantum computing? And so basically, you know, as you can see in that kind of header, like it gives computers a new set of rules. I think it's something that a lot of people don't understand. This is a, you know, an actually completely different, like completely different paradigm of computing, right? So we're not just, you know, taking regular computers and putting some stuff in regular computers and changing them up a little bit, right? This is an entirely new way of solving problems, entirely new way of manipulating matter in order to perform like algorithms and computations, right? And so one example of that, where we're talking about quantum machine learning, so for example, stuff like Monte Carlo algorithms, where you have to search through a giant, you know, you have to try a bunch of cases and kind of see where each of them lead you, right? And you have, you know, you might have billions or trillions of different cases that you're trying, right? Quantum computing can kind of result in, for lack of a better word, a sort of parallel processing ability. And I'm not talking about like parallel processors as in you have a bunch of cores in your processor or whatever. You have threads that you're sending to each of your cores. I'm talking about, you know, doing stuff in parallel as in, you know, each of these possible scenarios. So like, for example, the traveling salesman problem, right? Some of you might have heard of that, where you have, different routes that the salesman could take, right? These quantum computers are actually performing all these simulations of each different path. I guess basically at the same time. They're basically performing all of them in parallel. It's a little tricky to describe, but that's kind of the gist of it. We also can have more accurate quantum simulations. So, for example, if you're simulating a drug interaction, you're talking about a quantum system, and you're trying to take a quantum system and simulate it using ones and zeros. So quantum computers are fundamentally different from that. And they are, obviously quantum systems. So if you're simulating a quantum system with a quantum computer, one can imagine how that might be a little bit more accurate, or it might be a little bit faster, right? One very famous result, very famous potential application of quantum computing is also prime factoring. So a lot of people that came to tabling a couple days ago, we were talking, for those of you guys that mentioned you might be interested in cryptography, and you've heard of RSA encryption. We'll talk a little bit later about what that is. RSA encryption results is dependent on the fact that giant numbers are really, really hard to factor. And there is a prime factoring algorithm that could be used by a quantum computer that could potentially have an exponential speed up over over what we call classical computers or regular computers. We'll talk about that later. The last one is more secure communication. So you can use the property of entanglement, quantum entanglement, to have theoretically perfectly secure encryption. So that's pretty cool. So let's see. So I'll talk a little bit about what quantum computing comes from. As I kind of mentioned earlier, right? Yeah, exactly. So that's Shor's algorithm is the algorithm that people use for quantum encryption, or for breaking RSA encryption. So right now, as I kind of mentioned earlier, right, this field is kind of in its infancy. It was not proposed until after 1980. So that's kind of, in the grand scheme of things, that's pretty impressive. That like fusion, for example, was proposed over 100 years ago, and they still haven't developed applications of it. So that's kind of an exciting thing about this field. It was proposed by I want to say Richard Feynman is often credited as the kind of discoverer of quantum computing. And he was definitely involved in the first quantum computing conference that they had. He was involved with kind of developing a paradigm for what that would look like. And then it wasn't until 1998 that even a single qubit, and we'll talk about what a qubit is, even a single qubit quantum computer was developed. So that's pretty cool. That's been what is that, 23 years or whatever. Since we even have had the first, most basic rudimentary version of this technology, and now we're at the point where, we can do a lot more sophisticated things with these. So for those of you, and I think, what I find funny is that a lot of people don't even know that we have quantum computers. Which is understandable, because the way that a lot of this stuff is reported in the news is a lot of hype, and people don't really know it's true or not. But we actually have had quantum computers for some time now, and we have a lot more sophisticated ones now. Still not sophisticated enough to do anything of much practical use, right? It's still kind of in a theoretical phase, but we do have physical quantum computers, right? IBM has, in a basement somewhere in Cupertino or whatever, has a physical quantum computer. So I think that's pretty cool. So before we start digging into a lot of what's going on in this field and all these developments, I don't think they're in Cupertino. They have labs in the Midwest or something. I'm not sure. Ishaan was asking. He says I don't think they're in Cupertino. So I just wanted to kind of give you guys a broad overview of the kind of parent field of quantum computing. So quantum computing is kind of a subset of quantum information science. And quantum information science includes a lot of things that kind of quantum computing doesn't as much. So for example, quantum simulation, you can do quantum simulation on a quantum computer. For example, Google, a couple years ago, they did the world's biggest quantum chemistry simulation on their quantum computer, a while ago, right? So that's something that quantum computers can do, but also what other people have done, and what some labs, I think there's actually, or there's a lot of labs even on the West Coast as well, at UCSD, at Irvine, UCI, and UCLA, USC, a bunch of labs all over the country are doing quantum simulation with basically, instead of using quantum computers, they're using different kind of exotic phases of matter. They're using these things called optical lattices, different kind of physical systems that they're using to simulate more sophisticated physical systems, right? So that's kind of a more general thing that includes quantum computing, right? You can do quantum simulation with a quantum computer, but it's also a little bit more broad, right? The second thing is quantum communication. That's kind of another adjacent thing to quantum computing. So for example, we'll talk about this later. China has put a ton of money into quantum communication, and it's not really quantum computing, right? It's a little bit of a different field. We'll kind of explain why that's different. Eventually, the US, the EU, and China all plan to have some sort of quantum internet within the next couple of decades. So that's pretty exciting. And the last one is quantum sensing. So, you're trying to sense whether an electron is somewhere or not. Having a quantum system that you use for quantum sensing can be really really useful, right? So that's a big field right now. As in general, technology and sensor technology gets better and better and better. Eventually, you're dealing with these quantum effects that you can't really deal with classical or non-quantum simulations and non-quantum sensing technology. So that's kind of adjacent to quantum computing. Quantum sensors are something that could maybe network with a quantum computer or be hooked up to a quantum computer, right? So we'll talk about the Quantum Initiative research labs. Those are really cool. So that's kind of an overview of what quantum information science is in general, of which quantum computing is kind of a small part, but one that does get a lot of hype. So this will be my last slide. I'm going to hand it over to Thomas after this, but I'd like to talk about, it's kind of a good transition because looks like someone just posted the quantum.gov website, right? This is their website for the National Quantum Initiative. So we're going to talk about that a little bit. A couple years ago, the U.S. government passed the NQI, and it's a $1.2 billion act that basically funds basic research in quantum computing, quantum information science, as we talked about, and related fields. So one big kind of consequence of this is they have these national quantum information science research centers at the national labs. So I think the link that got shared earlier, that's the link to the to those QIS centers. It put me. That's perfect. Yeah. So these are the QIS centers. The Department of Energy is establishing these research centers at national labs. And a lot of them are actually doing these really, really interesting collaborations with like private industry and with like universities and stuff. Like for example, I think Caltech and Berkeley and a couple other West Coast schools are working with the National Laboratory up in the Bay Area to do a big research project and build a quantum computer. So they got a lot of really exciting projects like that. And also, for those of you that are really interested in this and are deciding if they want to even pursue possibly a grad school in this field, having this big Quantum Initiative Act and having all this money being poured in might be able to help you out. You might be able to get a government scholarship or work in one of these labs at some point. So this is kind of good for people that are trying to get into this industry right now as, you know, human capital. And there's also, you know, speaking of these labs as well, we have these plans for a quantum internet. So we'll talk about what the heck that means a little bit later. We actually had a workshop on it last quarter, and we'll probably do something else on the quantum internet, because I think that's something that's really fascinating, has a lot of promise. But these national labs have plans to create a quantum internet that's based out of these labs. And this would be really, really cool, because it would be an almost unhackable, you know, theoretically unhackable internet. So that'd be really awesome. And then there's just a list of, you know, so you can kind of see how this field is pretty broad, right? They do research in quantum sensing, advancements, networking, computing, and quantum technology, right? So quantum computing is just one of the things that they do, right? Oh, actually, that's a good segue. We'll talk about that a little bit later. And in fact, I wanted to mention, we'll have a Q&A actually at the end of this whole thing. So if you guys have questions, you post them in the chat. I'll read them, and hopefully a lot of them we'll get to later just in the presentation. But if you want to wait until the end, we'll spend a little bit of time just answering questions. You know, trying to explain some of the stuff to you guys and see if we can help you guys know a little bit more. So we'll talk a little bit about what the most impressive thing a quantum computer has done so far. We'll talk about quantum supremacy. So yeah, so you guys can check out quantum.gov. It's the website for the NQI. And it's a good opportunity to kind of dip your feet or learn a little bit about what governments are doing with this stuff. So I'm going to hand it over to Thomas. He's going to talk a little bit more about some government involvement in quantum computing and what other governments are doing. So he's going to talk about China for you guys.
Yeah, so the NQI is basically the US's investment into quantum computing, but obviously the rest of the world is interested in it as well. And this is especially true for China. I mean, as it's saying here, China was the first one to launch a quantum communication satellite. In terms of quantum communication, they are really the top of the world. It's not even close for second place for the quantum communication. So the US and the rest of the world has kind of been playing catch up since the quantum communication satellite, hoping that, as sort of Ben was saying earlier, they don't get their perfectly uncrackable communication before we can get it as well. The third bullet point, as it's saying, China had quantum supremacy, which is a term coined to basically talk about when a quantum computer has done something that a classical computer can't. And that happened in 2020, so that was a big deal when that was announced. And sort of to reiterate the whole point of China being the top in quantum communication, they were the largest spender from 2012 to 2017. So sort of not the most recent years, but you know, before the US decided to launch their NQI, and as we'll see on the next slide, as the EU did as well, China was really the main people investing into this technology. So talking about sort of other government investment, another thing that the US did is in March of 2021, Biden talked about trying to get the GDP investment into science closer to 2% instead of at the like 0.5% that it's at now, and specifically mentioned quantum computing as one of the main targets of the increase in funding. Australia, UK, and the US have partnered in this sort of like AUKUS, AUKUS, I'm not exactly sure how you pronounce it. It's been in the news recently. It's exactly the partnership that France has been complaining about with the whole selling nuclear submarines to Australia. But going along, you know, it was not just a contract to sell nuclear submarines, it was also a contract to kind of bring Australia, the UK, and the US all under the same technology sphere, so that they share with each other their sort of like new tech, including, and you know, again, specifically mentioning quantum technologies. And then, right around the same time as the US's NQI, the EU committed €1 billion, which is approximately $1.2 billion, towards their quantum technologies flagship, which it is almost in essence identical to the NQI. So the EU and US, it's sort of unclear which one, who got the idea from who, but it definitely feels like one of them, posed this idea of committing $1.2 billion to quantum technologies, and then the other one was like, "That's a good idea. I'm going to copy that." So yeah.
Yeah, crazy stuff. It seems like a lot of world governments are jumping on this quantum computing train, so that's kind of cool to see. I just wanted to mention on this slide, was it this slide? So this satellite was able to do is, if you guys know a little bit about like what entanglement is, and even if you don't, basically what this satellite was able to do, this Mesius satellite, it was able to entangle these two photons together, so that these photons are kind of paired in what their measurement result is. So if you measure one of these photons, the other one will have the same result, right? Those photons were split up by the satellite, and they were beamed to two different parts of the world. I want to say one of them was in like Europe and the other one was in China. So like 4,000 miles apart or something like that. And they were able to test that these photons stayed entangled, through the atmosphere and everything from the satellite. So it's kind of a crazy result right there. That's something that I think the US government probably was pretty worried when they saw that. They're like, "Oh man, we got to get our act together." So that might be part of the reason they passed that act in 2018, right? And then, so talking about more generally quantum computing, and specifically the industry of quantum computing. So what industry players are doing right now, because that's kind of part of what we'll be talking about today. So IBM is kind of at the forefront as an industry player. They're putting a bunch of money into it, and they're building their own quantum computers. They have their own framework for programming quantum computers. This is kind of their projection that they've made. So, obviously take it with a grain of salt, right? Because you know how all these kind of projections can be, right? But they think that they're going to have, something like 400 something qubits by 2022, and they're going to have, 1121 qubits by, 2023. So we'll see if that winds up happening. But it does seem like this field has been growing really fast. So in 1998, the first quantum computer that they built had 3 qubits. In 2011, they had 14 qubits, and in 2019, they had 53 qubits. And these are, pretty solid qubits too. They're have, we call long coherence times. They're able to be isolated. We'll talk a little bit about what that means later. But that's kind of where this industry has been going. A lot of people didn't expect this quantum supremacy thing. So we'll talk about that. That's something that just came out, a couple years ago by Google, where they are able to do tasks on a quantum computer that a regular computer, even the supercomputer, can't do. So I think that's pretty crazy. So we'll talk about that. So Google, in 2019, in October, the paper was leaked by them that basically demonstrated that they had achieved what they called quantum supremacy. So quantum supremacy is, as I said, right, is doing a task that even the most powerful supercomputer in the world can't do, or would take hundreds of years to do. So they were able to do, find some little specific algorithm that only a quantum computer could do. Right, it involved recognizing whether a number was randomly generated or not. Right, this algorithm, even though it has no practical purpose, a lot of people thought that this was really significant as like a proof of concept idea. That the fact that quantum computers can even do something that a classical computer can't, right? Because we didn't even know that was necessarily true, right? A lot of people thought, well, classical computers, regular computers will just keep getting faster and faster, and quantum computers will never catch up. So this kind of proves that that's not necessarily the case. In fact, in the last couple years, two different Chinese research groups. One, I think, one government research group that was using a similar technology to Google, and then also a Chinese, I think, at a Chinese university, a team using optical qubits, which we'll talk about what that means. They were able to do an even more sophisticated algorithm. So these two teams at China, even if there was doubt as to whether or not Google's original demonstration was technically quantum supremacy, or if you could have figured out a speed up for that algorithm on a supercomputer. What these chips are doing, these quantum computing chips, are pretty far outside the reach of anything that's possible with a regular computer. So that's very exciting, very cool. That this stuff is not even possible on a regular computer. It would take thousands of years. So let's see. So we're just gonna, and then we'll talk about like some applications of quantum computers. So I think we talked a little bit about RSA encryption and chemistry and encrypting data with quantum computing. We're just going to go a little bit more in depth in this slide for those of you that are curious. I think some of you guys might have backgrounds in a little bit of cryptography, or if you're CS majors or whatever and you're interested in cryptography. That's a really big field right now. So RSA encryption, basically, a very kind of a very rough overview of what RSA encryption is you take two numbers, right? Two giant prime numbers, and these are, numbers with hundreds and hundreds of digits, right? You take these two prime numbers and you multiply them together, right? And you get some giant number, right? Thousands and these thousand, giant number, right? With thousands of digits and everything. That number, if you have one of those prime numbers, right, then you can factor this giant number, right? Because that giant number has two factors. It's, those two prime numbers, or I guess four, those two prime numbers and then one in itself, right? But if you don't have these two prime numbers and you just have 1,000, digit number on your computer, you might find that it's actually very, very, very difficult to factor that number. And every time you add a digit, right, that's you multiply by 10 the amount of numbers you have to check as factors of that number, right? So we call that in computing, we call that an exponential complexity, right? So the complexity of the task that you're trying to accomplish increases exponentially with how many digits you add to this number, right? And that's very, very useful, because if we add enough digits to these numbers, we can get to a point where no computer in the entire world can figure out those two numbers that go into this giant number, right? These two factors there. Quantum computing has the potential to change that a little bit, because quantum computing might be able to factor these giant numbers much, much, much faster than a classical computer. In fact, they might actually be able to do them in what we call polynomial time. So they might actually have what's called an exponential speedup over what regular computers can do. And what that would mean is, if you add a digit, you add a few qubits, you make your quantum computer a little bit more powerful. And you add another digit, you make your quantum computer a little bit more powerful, right? You have to double the power of your computer every time you add a digit, right? So this scale up is that's a very significant difference in scale up. These actual algorithms, they already exist, and they would be useful if we could use them. But as I said, we have something like 50-something qubits or 70-something qubits in the state-of-the-art quantum computers today. These algorithms would require something like 2,000 qubits, right? So we're not anywhere close to actually doing what we call Shor's algorithm, which is the algorithm for factoring these numbers. That algorithm probably won't be able to be performed on any giant number anytime soon, right? It's going to take a lot of evolution of this technology, but it does have the potential to do that once we can get 2,000 qubits or whatever, and that's kind of crazy too, because we might need you might need in the order of like teraflops or whatever on a regular computer to do these kind of operations. And we're talking about 2,000 kind of logical units on a quantum computer. So it's kind of really it's a lot compared to what we have so far, but it's actually not a ton compared to how complex, you know, a regular computer is. The second thing, I'll talk a little bit more about quantum chemistry. So basically, you know, you have, you know, I guess a quantum chemistry simulation is basically you have all these fixed points, right? You have your nuclei, and you know, they're essentially fixed, and then you have, you know, obviously it's chemistry, so you're dealing with electrons, right? You have all these electron orbitals in these different, you know, atoms, and they're all interacting, they're all overlapping, and they're creating some sort of wave function, some quantum function for the whole system, right? Every time you add another atom, you add another set of electrons, you add another complete set of interactions. You have to consider that electrons, you know, the interaction of these electrons with this atom and this atom and this atom and this atom, right? Every atom in the system, when you add another particle to it, it you know, increases exponentially in complexity. If you can think about what that means, right? Where we have to derive a whole new set of equations every time we add something to it, right? It increases like that. So quantum computing, as I said earlier, right, we're dealing with a quantum system being used to simulate a quantum system, right? So instead of, you know, going down the route of every possible combination that we could have of electron orbitals, for example, like, oh, let's see if we, you know, let's see if we can find the lowest energy combination of these electron orbitals, right, the interactions of them. Well, your lowest energy might be over a hill where that is higher energy, and you might get halfway up that hill in your, you know, whatever algorithm you're using on a regular computer, and you might decide it's too much computing power. You don't have the power to you know, explore the full contour of that energy, right? A quantum computer would allow you to kind of, you know, without fully explaining it, right, because it's something that I'm not even sure I understand, but it would allow you to basically, you know, explore that landscape, that contour, right, that kind of that graph of those energy levels, right? It would allow you to explore that multidimensional graph in a way that was kind of all at the same time, in a way, right? So just as that physical quantum system exists in all these different states at the same time, right, a quantum computer can exist in different states at the same time, right? And it allows it to explore that space, right, that energy space, a lot more efficiently than a regular computer. So that's really a big potential for that. The ultimate goal of quantum chemistry, at least in my opinion, is for anyone to be able to come up with some idea they have for some chemical interaction or even a drug. You know, that's a big one that's people have brought up, right? You can be you know, just some scientist in a lab somewhere at UCSD, for example. You can come up with the idea for a drug, and then you can go and log into a quantum computer, access it through the cloud somewhere, right? And simulate that drug and see what result you get from that simulation, as opposed to having to actually synthesize it and try it in a petri dish, right? So that's something that could kind of blow open, the same way people say with 3D printing, it blows open the field of manufacturing a little bit once it gets cheap enough. This could possibly have a similar effect on medicine, right? Because you don't need to have all these resources to synthesize new drugs, right? The new Breaking Bad, yeah, exactly. I don't know if I would encourage you guys to try and synthesize those kind of drugs, but that is definitely also a possibility. And then the last thing we're going to talk about is just kind of end-to-end encryption. So we talked about China's satellite, where they have these photons that are in entangled states, right? And you can distribute those photons to different people. So having a, I guess I could probably explain this to you guys, right? So Jesse, what happened to the quantum computer? Exactly right. So you can maybe imagine it this way, right? Quantum entanglement basically says that I have two particles, and if they're entangled, right? If they're undergoing quantum Berg entanglement, right? Then those two particles, when you observe one of those particles, when you measure one of those particles, the other particle will get the same. You'll get the same result for that other particle, right? So that's like a really strange effect, because it turns out that can exist at any distance, right? You can have a particle, I can have a particle across the universe from one of you guys, and I can measure my particle, and once I measure my particle, I'll know for 100% fact what state your particle is in before you even know that. So that's almost like an instantaneous transmission of data. We can almost think about it like that, right? That's what kind of disturbed Einstein. He talks about spooky action at a distance, right? Quantum entanglement is just so weird, right? But it turns out you can't actually send information faster than the speed of light. But we'll talk about that maybe in another workshop. But basically, the idea is, right? Let's say if I have one of the particles that's in an entangled pair, and then you have another particle in this entangled pair, then we can observe both of our particles. We can measure both of our particles, and we can not tell anyone, right? And we can get a cryptographic key now that we can use because we know this key and no one else does, right? That's what enables cryptography, is you have a key that you and the other person you're sending data to know that no one else knows, right? And you can actually, instead of deriving that key beforehand, instead of writing it down, being like, okay, we're going to use this key, right? We can basically have a bunch of pairs of particles, and we can keep those particles entangled until we decide that we want to send some information. Then I can measure those particles, and then I can send information to you using those measurements as a cryptographic key. So I know that's pretty tricky stuff, pretty complicated stuff. So I understand that that's kind of tricky to understand. But for those of you that have a little bit of cryptography under your belt, that have seen some of that, that hopefully that makes a little bit of sense and maybe helps you understand how mind-blowing this technology is and how it would totally revolutionize cryptography if we could develop it. So that's just a couple applications of what this stuff could do. And then finally, just quantum computers will probably always exist in the cloud to a certain extent, right? Because they have to be cooled to like almost absolute zero, incredibly low temperatures. They're superconducting circuits, so obviously just have to be at really low temperatures. It has to be isolated from anything sort of like vibrations or sound or light waves or anything, right? So this is stuff that you can't necessarily, at least we don't think, we probably can't have it in our phones or whatever. We might be able to have eventually, but for now, in the near term, these things are going to be in big, basements and like IBM or at, universities or whatever. And this, Mike asks, this involves a lot of quantum physics, right? That is definitely true. This does involve a lot of quantum physics. However, the quantum physics is not necessarily the entirety of the field. So, for example, there's quantum algorithms and the programming of quantum computers, and that is a little bit divorced from the quantum physics, right? We can take the math of what you can perform on a quantum computer, and we can divorce it from the hardware. The same thing we do with computers, right? If you're a Python developer, you don't have to know how a shift register or registry works, right? Same thing with a quantum computer, right? IBM has released this program Qiskit, this Python library that you can use to program quantum computers, and you don't have to know what type of quantum computer it is, right? You can just program this thing using these mathematical abstract rules, right? So that's something that's really exciting, is that even if you're not interested in the device physics kind of aspect, you're not interested in how these things actually physically work, right? You can still learn how to do some really, really useful stuff on a quantum computer. So I think that's really cool. So let's go to the next section and talk a little bit about what a qubit is. So I mentioned qubits earlier, and I haven't really explained too much of what they are, right? So a qubit is a quantum kind of analog of a classical bit. So hopefully at least a lot of you guys know what a classical bit of information is, right? We have, as far as we physically on a actual computer, we have a bunch of CMOS MOS capacitors, and those things have charges stored in them or don't have charges stored in them. And the charge is 1 and no charge is a 0 or whatever. We have some hardware implementation, but basically you just have these things, these mathematical objects that you can divorce from the hardware, right? And those things exist in a 0 or in a 1 state, right? You can also have analog regular computing, right? Analog regular computing, you can think about it as you have like a dial where you can turn up, from 0 to 1, as opposed to having discrete states, right? A discrete computer, you can have an analog computer that you can turn up like a dial, right? One way I like to think about it is like coins. Like a bit is basically a coin that's either heads up or tails up, right? A quantum bit or a qubit is a little bit different. A qubit, one way I like to think about it is as if it's a coin that's spinning. So it's not like an analog bit where it's kind of heads. You can kind of tilt it a little bit, right, and put it in that state, and then it's tilted at like kind of heads, kind of tails, right? It's half heads, half tails, or whatever. A spinning coin is not in a state of heads, and it's not in a state of tails either, right? It's in kind of a different state where it's sort of in heads and sort of in tails, right? That's kind of I think my favorite analogy for understanding what a qubit is, because I think it really helps it conceptualize. And you can imagine if you have all these spinning coins, right? You can have them all interact and do things together, and at the very end, you can kind of go boom, and you can flatten them, and you can put them back into their regular states of ones and zeros, right? So that's kind of an analogy I like to use for what a qubit is. Just like in a regular computer, we have our abstract ones and zeros, right? Even if you're writing a compiler or something like that, you still don't really know what's going on physically. But you also have, the actual physical thing that's being implemented. So for example, qubits, we can implement them using any two-level quantum system, right? So just like a classical bit would be a system where it can exist in, two different states. It can be, for example, an electron or no electron, right? A quantum system, a qubit, can exist is any quantum system that can exist in two states. The difference is those quantum systems exhibit what we call superposition states. So they exhibit these states kind of like a spinning coin, where it's not really in one state or the other. I'm sure you guys have heard of, right, Schrodinger's cat. That's an example that a lot of people like to give for what these entangled states or these these superposition states are. And that's actually not too far from the truth. A qubit is basically a tiny little Schrodinger's cat, right? It's a system that exists. You're not really sure if it exists in the one state or the zero state, for example. So one example that we like to use is like the spin of an electron. So if you guys have read a little bit of about physics, you might know that electron has a spin, and that spin is either in the up state, right? It's either that spin vector is in one direction or it's in the opposite direction, right? So that electron can exist in a superposition state where that it's almost like a spinning coin, right? It's not in the up state or the down state, right? It's in something kind of in between. That's not really either or, right? Same thing with photon polarization. So a photon is an oscillating electric and magnetic field, right? Electromagnetic radiation. That magnetic field can oscillate, horizontally or vertically, or it can oscillate horizontally, right? And we can, and it can kind of be somewhere in between, right, where it's not really oscillating horizontally or vertically. An inductance of a Josephson junction, that's what they use for these transmon qubits at Google and IBM. That's kind of I actually have been reading about that a little bit lately, and that stuff is crazy. That's PhD level, materials science stuff. So if you guys are interested in that stuff is really cool, but it's definitely a little bit beyond maybe the undergrad level. Two-level atoms, so you have your energy levels in an atom. You guys remember learning about that in chemistry, where you excite that atom, you launch a photon at it, and goes up to an energy level, and then it releases a photon, goes back down, right? You can have these superpositions of these different energy levels. And then interferometry, which is basically just manipulations of photons. So we're taking light and we're doing things to it, and we're using that to implement qubits. But I guess the overall takeaway of this is basically that just like a regular computer where you can do operations on any type of regular computer, people even build like regular computers that are based off of, pneumatic, pressure and stuff like that, or optical chips. There's different hardware implementations you can use, but you can run the same software theoretically on a regular computer. So quantum computers are similar in that you can run any quantum software on any quantum computer, theoretically. So that's something that's really cool, and that allows us to kind of, for those of you guys that are, computer science people that have that background, that allows you to do some really useful stuff with quantum computers without understanding what the inductance of a superconducting Josephson junction is, right? And then finally, there's different formats that people have prescribed for quantum information science. So Q-trits, which are like 3-level quantum systems, Bose-Einstein condensates, which are basically extremely cold pieces of matter that kind of have wave functions that overlap and create really interesting effects that we can study, optical lattices that let us simulate, crystal lattices and stuff like that. So yeah, really crazy stuff. The idea is we have 2-level quantum systems, and they exist in these superposition states. That lets us do some really useful stuff with them. So I'll actually so we're actually going to talk a little bit about the hardware for those of you that are interested. This stuff is really, really cool. This is more up my alley personally. I'm more of into the hardware side. So we'll talk about. I just have a couple slides on these. So we'll talk about those for those of you that are interested. I encourage you to read a little bit about this hardware stuff if you're interested, because this stuff is really cool. And for those of you that are physics or electrical engineering majors, you might have a chance to actually work on some of these really crazy systems. So first of all, we have these superconducting transmon qubits. So that's what IBM and Google use. And they have these things called tunnel junctions between two superconducting islands. So they have, 2 pieces of superconducting material. They have a little thin insulating sheet between them. And then these superconducting electrons, they form something called Cooper pairs, where they oscillate with certain energies, right? And then they use these distinct oscillation states to implement qubits. So the idea is, right, we have these crazy hardware implementations, and winds up being pretty, maybe more simple software that we can use. And then I think Ishaan was going to talk about trapped ions a little bit.
Yeah. So trapped ions, basically the way this works is that you can suspend ions in free space using electromagnetic fields. So they're just suspended there, and they're not interacting with anything else. And so qubits can be represented by the electronic states of the ions, and those electronic states can be manipulated with lasers to manipulate the qubit states.
Yeah, and then I think Thomas is going to talk about. I'll talk about NMR, nuclear magnetic resonance. You guys can read that, kind of peruse those bullets, right? Basically, you have a molecule, and you have different atoms, and those atoms, their electrons have different spin states, and those states can be driven. So you can shine light on that molecule. And different electrons in different atoms will get excited by those photons that you send there, right? And that's going to be able, and you can manipulate those in order to get some sort of qubit-like interaction. So you can actually do quantum computing with these things, with molecules in basically in a jar, right, in a cavity. And then I think Thomas was going to talk about the last couple.
Yeah. So first, optical qubits. They are based on the probabilistic nature of photon polarization, just sort of exactly as Ben was saying earlier. Optical qubits are typically implemented with single photons, meaning one photon is one qubit. But there are some examples of entangling multiple photons and using the entangled group of photons as a single qubit. And the reasons you would do one versus the other, the entangled photons are obviously harder to create because you have to get multiple photons and then entangle them. But after you have that group of entangled photons, it's more stable. They're easier to deal with when it comes to like measurement and manipulation. And now the main drawback of the optical qubits is obviously you're storing information in photons, which how do you store a photon? You know, like you can't really, it is just a propagating oscillation in the EM field. So that's sort of, they're often paired with nitrogen vacancy centers for storage. So to talk about nitrogen vacancy centers, basically what these are is it's the empty space in a diamond lattice created through substitution of a nitrogen atom for a carbon atom. So just because nitrogen atoms have more valence electrons than carbon atoms do, if you substitute a carbon atom for a nitrogen atom, you actually kind of end up taking out two carbon atoms, and in the place you'll get one nitrogen atom and then a hole. And so that hole is the nitrogen vacancy center. What it allows you to do is you can sort of store the light, you can store the photon qubit in the nitrogen vacancy center as sort of like an excitation of the unpaired electrons in the vacancy center. And so obviously, you know, these are excitations from the EM fields, you know, sometimes with microwaves, sometimes with visible light. And really what it allows you to do is just as I was saying before, it allows you to store those optical qubits. And so it's talking about coherence times there, and I think we've touched on it a little bit in this presentation, but the coherence times are basically just the storage time. You can think of it like if you had a regular computer, or like if you had a USB drive, but your USB drive automatically wiped itself after a certain amount of time. So whenever you're doing some sort of calculation with quantum computers, eventually they decohere, which sort of essentially means they wipe themselves clean. And so if you don't finish your calculation before they decohere, you get no answer out. You'll just get like garbage. So the longer the coherence time you have, it means the more complicated calculations you have. So increasing coherence time is one of really the main pushes for improving quantum computers, on top of course, increasing the number of qubits and decreasing the noise, or also known as decreasing the error.
Yeah, thanks, Thomas. Thomas actually did a lot of research into this, the last two, optical and NV centers. If you guys are interested in this, like device physics, maybe more physics or electrical engineering or nanoscience kind of route, there's definitely going to be a lot of jobs and a lot of people trying to find people that are qualified to work with this kind of stuff. So if this stuff interests you guys, and you're interested in maybe going to grad school, getting a master's or something like that, and really digging into this stuff, this is a really cool field. Or if you're interested in superconducting or superconductivity, for example. So yeah, I think we're almost done here. So we got 2 more slides for you guys. So bear with us for these last couple. It'll I know this is we try to keep it pretty non-technical today, but I know it gets pretty tricky when we start talking about all this crazy hardware stuff. So we're just going to talk about why quantum computers are not yet in your desktop computer or in your cell phone, right? Talked about that a little bit earlier. But part of it is that we need really precise measurements, right? So we need to be able to like record the magnetic field emitted by something by within some tiny margin of error, right? So not being able to do that perfectly is going to make it a little bit difficult. These systems have to be super isolated. So I want to say, so I think IBM systems are cooled to something like 10 millikelvins or something like that. So this is 10 thousandths above absolute zero. And a lot of systems, a lot of the people that are doing research in this, including the lab that I was able to intern at this summer, they're doing stuff on the order of like nanokelvin, right? So they're, what is that? That's a billionth. No, it's quadrillionth of a degree, right? Is a nanokelvin. So that's pretty crazy that we're all the way down there to almost absolute zero. Some of the coldest matter in the entire universe, as far as we know, is in some of these quantum computing labs. They have to be isolated from noise. They have to be, any little particle, any photon, any piece of, cosmic rays or whatever that interacts with these systems, it's going to cause them to, as Thomas said earlier, to decohere, right? So we're not, so they wind up getting entangled with the outside world, and they kind of they lose their coherence where they're all in this state together. It's also very difficult to store these, right? They kind of fall apart very quickly, and error correction is very difficult to do. Some error correction methods have been created, but the level of error correction we have with regular computers, where it's very, very rare. Every once in a while, you'll hear a story about some crazy thing that happens because a cosmic ray strikes a hard drive somewhere, right? But generally, that doesn't happen with regular computers, right? Their error correction methods are really, really, really good, and we don't really have to worry about them anymore as much, right? It's definitely not true with quantum computers. So if you want to be like one of the people that developed the first error correction methods for regular computers, in the 60s or whatever, that might be something that's interesting to check out with quantum computing. You might get your name on a some technique or something like that for error correction. And then a lot of quantum computing algorithms haven't even been written yet. So for those of you that are interested in the computer science aspect of this, that's a great place to start from. Even if you're not as interested in the hardware, you're not as interested in all this superconducting stuff, right? If you're interested in algorithms or cryptography or machine learning or AI or any of this stuff, a lot of these, we just haven't. The Qiskit, for example, that IBM developed, hasn't been around for more than a few years, right? So there's a lot of stuff that could be written for a quantum computer, once they get powerful enough. And we're just not going to have enough software engineers, enough people with the interest or the knowledge to actually do useful stuff with these things. So that's something that there's a big void in kind of talent right now. So if you guys are interested in that, that's something that would be really awesome to get into. Hopefully if this technology winds up being as successful as people think it will. And then last thing, we're just talking about what you guys can do to get involved in quantum computing in general. You can join us, but you can also you can check out Qiskit. Qiskit is IBM's software for quantum computing. You can keep attending our workshops. We're going to be going in more specifically into some different kind of aspects of quantum computing. You can join our Discord. That link is going to be, I guess I can send that link to you guys. There's the Discord link right there. So if you guys want to check that out. Oh wait, I have to wait. So yeah, if you guys join our Discord, I assume a lot of you guys kind of saw this through our Discord, but for those of you that haven't gotten a chance to join us, that's a great way to get involved with us. And then, whoops, we have our GBM, our general body meeting for the fall, is going to be next week at the same time, right here on Zoom. We'll post a link to that on the Discord. We'll promote that and everything. We'll ping you guys. So if you guys are interested in specifically in getting involved with us, that'd be a great way to get involved.
Yep. Hopefully more of us officers will be there next week.
Yeah, exactly. So you'll get to meet more of us, hopefully. And then the last one, there's just an article that is a really, really good introduction to the math behind quantum computing and kind of the abstracted kind of software stuff that you can do, so you can learn about what a qubit is, the same way that you would learn how to do abstract mathematical operations on a regular computer without knowing how transistors work, right? you can do this. You can do this on quantum computers, and then yeah, just see if you guys get involved with us. Will be a lot of opportunities to start getting involved and really learn more about this really cool field. Someone asked if there's going to be any chance to have this meeting in person. Unfortunately, the Center for Student Involvement, I guess we have a personal vendetta against them because we put out all this effort trying to get all our events in person and everything, and get like funding and rooms and reservations and everything. And then we found out a few weeks ago that everything is going to be virtual until after week 5, and we're guessing probably for the rest of the fall quarter, unfortunately. So stay posted. Hopefully we'll be able to do in-person stuff at some point pretty soon here, but unfortunately we can't give you the answer to that one. And then where are the links of Qiskit in the article? So let me send you guys these links real quick. So this is Qiskit right here. This is IBM's kind of quantum computing framework. They have a really good tutorial as well on their website. They have a textbook, but it's actually very good. It's not as dry as you might expect a textbook to be. And they also just have a lot of opportunities to get involved in general. We have a Qiskit workshop planned pretty soon here, so stay tuned for that. We'll teach you guys a little bit about what Qiskit is and how you can get involved and how you can learn about it. And this last one I just sent is this Quantum Computing for the Very Curious. It's an article written by Michael Nielsen, who co-wrote basically the big book on quantum computing that most people use for like quantum computing courses. And he actually does a really, really good job. He's been working on how to teach quantum computing for years now, and he's starting to get really, really good at it. And so this article is just kind of a great just introduction, and just really well put, takes you through all the basics. You don't have to know any prerequisite knowledge, so it's really, really cool way to get involved. So finally, I'm going to open it up a little bit. I know some of you guys asked questions during the workshop, so I'm going to open it up for a little bit if you guys have anything to ask or anything that you're curious about. Ishaan just put a feedback form in the chat. We would love it if you guys could fill that out and give us some feedback on this event. Tell us how we did, right? Obviously it is a Zoom event, so unfortunately we wish we could give you guys a QR code for a feedback form on an in-person event, but this is the way that it has to be during these times, right? So if you guys can fill that out, that'd be awesome. We'd love some feedback about these events. We always are trying to improve ourselves, right? And we're a new organization, so we haven't gotten our event flow perfect yet. So yeah, let me know if you guys have any questions. I'll open it up for a little bit. Kind of sit here for a sec. Let's see if you guys have anything you want to ask. Feel free to turn your mic on if you want. No questions. I'm not sure. That's okay if we don't have questions. This is a lot of information, so I totally get it. I totally understand. I know I've done that many times in like physics class, where you have like the professor does some lecture, and then you like listen to it, and you're like, there are like questions, and you're like, I can't even formulate a question. Like I don't even understand it. So I get it. Hey, thanks, Connor. Yeah, I appreciate it. Well, I hope you guys. Yeah, so I hope you guys enjoyed yourselves. Hope you guys got something out of that. I tried to make it as non-technical as we could, right, so that you guys can understand this stuff. This stuff is pretty tricky, but it's also not as bad as you might think it is. So I would encourage you to hang in there. Maybe attend some of our other events and see how you feel. So we'll hang out for another 10 minutes or so and just kind of just keep our mics on and cameras on and stuff. At least I will. And if you guys want to ask any questions or say hi or whatever, yeah, let me know. Thanks for coming, guys. I'm going to turn the recording off, though, at this point. Yeah, thanks. Glad you guys liked it. Stop recording.
The recording's still on.